Callum's going to talk to us about some robots that he's going to work with at work, aren't you?
I am.
And you're going to do some live stuff.
Live demo.
So that'll never go wrong.
Can't be as bad as matters, surely.
Let's see.
I
think you need to touch some wood right now. Yeah, okay.
No, that's real.
There's no opinion. Right, well, thanks for your coming. Thanks Code Movers for the space, really appreciate it, guys. And thanks to Chief Funk, I know he's not here tonight, but thanks to him for the pizzas and sponsoring us on that front as well. No news today, is there? No news. No news then. So we'll get started. I'll hand over to you.
Cool. Right. So I'm going to quickly bring up my. It got closed. Beautiful. So yeah, talks on tracking an autonomous robot. We have an autonomous robot, and we need to track it so that we know what happened to it, or know what it did, whether it got stuck, whether somebody crashed into it, things like that. I'm not joking when I say somebody crashed into it. So we had a project a few months ago now to be able to kind of surface some of this data. We have an application that has all this data already, but it's all very ephemeral. It happens, and then once it's gone, can't get it back. So it's all about trying to surface all that data that we've already got so that we can go back however many days, or weeks or months, and go and find it again, basically. So that's what this talks about. What I'm going to do quickly is I'm going to send the robot off to do some missions, which basically means, I'll explain this a bit later, go and scan some aisles, basically. So let me send it on. Send this off a load of times. It will run in the background whilst I'm talking. Might get stuck. We'll see. The very nature of a robot going off in the background. So I'm Callum. I'm a front-end dev at a company called Dexory. We do Dexory does sort of analytics for warehouses. We were called Bots and Us, and then they changed to Dexory, which is sort of dexterous and inventory, I think. I can't remember, some think tank name. But yeah, so we have an autonomous robot that goes into warehouses. So if you think of Amazon or Maersk or any sort of big logistics company, or any company that has a massive logistics needs, like IKEA or Samsung, things like that, we go into their warehouse and we scan the racks and all their pallets, and we tell you what's actually there, basically. So I've been at Dexory for about 2 years now. Been in sort of the dev world for over 10 years. Most of that's in front end. I don't like DevOps, so I try and stay as far away as I can. I particularly like React, and according to the photo, I wear ripped jeans, which apparently more than I realised until I put that photo there. So yeah. So Dexory, here's a nice little animation that I've taken from the website. We have a base unit. There's lots of other alternatives from competitors who use drones, which are kind of, in lack of any other words, inferior. We scan every single column, every rack all at once, which means that we can get huge amounts of numbers. We can scan, I think we do about 100,000 kind of locations in about 24 hours, which is massive. Take all that data and then we put it into a system, and we can surface what the company or the warehouse thinks all the pallets are, and we tell them where they actually are. We can kind of do a lot more around volumetric analysis and things like that, and say, well, your warehouse is only half full, either the pallets are only half full, or there's kind of half your locations are empty, or a mix thereof, and then we can obviously offer solutions around that based on that data. So We have what's called a digital twin. So a couple of months ago there was a talk on digital twins. We have one here that is a representation of the warehouse that's going around, and then we can know where everything is basically. It's a nice little bit of blur from the website, but yeah, as I said, the robot goes around, scans warehouses, and let's see if I can play this for you, and goes up to about 16 meters, 14, 16 meters. We're working on another robot that has an 18-meter tower, which gets to about 20 meters high. So yeah, some of these warehouses are huge. We had one warehouse a couple of months ago that's over 1.1 kilometers long, just that one building. So some big places. So the problem set, as I've sort of outlined already, is around the robots will go off autonomously, and we don't know what's actually happening to them. We have lots of metrics and things like that. We have lots of alerts, so we had some visibility of things, but we wanted to really surface that and know, to be able to go back to a particular point in time and know the exact state of the robot at that point, and the history of what happened slightly before and slightly after. We have situations where forklift drivers will drive into the robot because they're not looking where they're going, and given our robot's about half a ton, when they shunt it a few meters, it's not a small collision, and it's important for us to be able to kind of know when that happens. We obviously get alerts for like accelerometers when things like that happen, but being able to go back to know exactly where the robot was, what the robot was doing, all those things, what led up to it, is obviously really important. So I, being a front-end engineer who was focused on the front-end side of this, me and a colleague built this. A lot of it was taking the data that we already had, being able to store that in an efficient way, and then having a UI that made it easy to surface that information and make it comprehensible to be able to see at any given moment. And this is what we came up with. So I just want to sort of explain a few things here. We've got the cameras, so the front, rear and tower. It's fairly self-explanatory, although rear is a bit kind of a misnomer because the robot can drive forwards or backwards. It just does what it kind of needs to. If it doesn't need to rotate 180, it only needs to rotate like half the amount, then it's just easier. I'll just do it backwards. We've got the map. This is a completely sort of 3D environment. We can see where it is exactly on the map. This is a nice small warehouse, so nice and small map. Big warehouses. There's obviously much harder to find sometimes, so it's some useful stuff. Being able to zoom in on the map particular areas. There's also like map annotations which aren't shown here to say like the robot can't go here, the robot can't stop here. If you're in this particular area, make lots of noise with lights and sound and stuff. If it's going past a door that people walk through, stuff like that. And then we've got things like the robot state of where it is, its tower height, battery, and all that. And then a few sort of things on the inside. You can see around date pickers to find where you need to go, and a lot around kind of conversions, because there's the location where you are and where the robot is, and obviously UTC that would sort of arm around, and they might be 3 different values. So we could be in BST, UTC is obviously 1 hour behind that, and the robot could be in a completely different country in a different time zone. So it's important to know, be able to tie up all the different time zones or timestamps that you've got, that when a person says, oh, it happened at 5 o'clock, did they mean it was 5 o'clock in their time or 5 o'clock in UTC or the robot? Things like that. So this makes it really easy to know what the conversions are, basically. So I want to break it down a bit about, take that and just narrow the problem set down about what we're actually looking at. So we're going to focus in on sort of the robot state, which is just these pieces of data here. There's a lot more, but just for this kind of subset. And I want to look at the battery. So battery, as you imagine, it's on a charge, it goes up. It goes out and scans, it goes down. It goes back to the charger, sort of, up and down, over and over again. Which is a bit like that. Goes up, as it's charging, goes off, does some missions and scans, goes back down, goes back to the dock, comes back up. And so that is just a particular point in time on that graph, which essentially means that that is just a chart. Doesn't look like a chart, but that's what it is. It's all time series data, which is what a chart is. We just happen to be looking at one very specific point in time, which is a particular second. So we update all the data, we save it every second, so 1 hertz if you like. We could obviously do that more frequently, we could do it at different frequencies for different pieces of data. Obviously images are a lot heavier in weight than just these snapshots of little bits of JSON, so we might be able to update the JSON more often and take up less disk space. It's worth noting that the robots are sort of entirely independent from all its compute power. So obviously it sends stuff out to sort of the customer-facing application via Wi-Fi or 4G, depending on what it can connect to at any given point. But ultimately, the robot is running all of its computation, and all of this data lives on the robot. It doesn't live elsewhere. So when we connect to it, we are physically connecting to a server on the robot. We're not connecting to sensors that go off to the cloud and do that. So one of the constraints that we had with this project was around storage space. We have a hard drive on there, but we have a lot of uses for it. This data can take up quite a lot. And then we've got ROS bags that we need to store, which is like snapshots of all the robotics side of things. We've also got LiDARs, and then we just need some like buffer memory, buffer storage for scanning, so that as the LiDARs scan, we can save it into there, and once it's finished, delete it. So you need a bit of buffer and things like that. So even if you've got 500 meg, terabyte, 2 terabytes, whatever it is, you can't use all of it because you need some of it for buffer. So, so having different sort of storage rates for different bits of data gives us control on how long we need to store this data for, before we can then upload it into a more permanent solution like an S3 bucket or something like that. But yeah, so we've got a glorified chart. It's all time series data. We save it every second in a nice order. If I asked for an hour's worth, I would get second increments and do that of over the hour, which would be quite a lot of data. And we can go back days and weeks. So how did we actually build that UI? And again, if we break it down, there's 2 parts of it. First is showing the data. That's nice and easy. We can do things like mock the data and just build a UI as you normally would. Any website will have some data. You can build components, and if I go back to full screen, like you've got a div for lights, and then you've got a badge for on, and depending on the state, if it's on, it's blue, and if it's off, it's grey. As you can see, the cleaning fans. Same for the battery. If it's above 50%, it's green because it's good battery. If it's 25 to 50, it's orange for warning. If it's below 25, it's red. All sort of UI things around state that is easy to manage. So the first is just being able to get the data. So we use a library called React Query. It just makes querying sort of async data a lot easier. I didn't realise there was quite a lot of glare when I chose a dark background, but hopefully you guys can see it. Technical problems. Let's see if we can
Try to do it.
just adjust the lights.
I don't know whether we're going.
So like I said, we use a library called React Query. What it does is it just helps handle intermediate states. So when you're fetching from a server, even though the front end, well, the client isn't, but when you're fetching from the client to the robot, to a server, there is some time before, well, when you make the request, before it returns. So anyone who's done async data, this is fairly obvious. There we go, thank you. So we have, React Query just handles that intermediate state. If there's an error, it'll tell us. If it's still fetching, we can show a loader and things like that. So it makes it easy. We specifically, in this case, use an infinite query. And basically all that means is that we send a request, and then when we tell it to send another request, it attaches the second request onto the first one in an array, or an array of arrays. So a prime use case for an infinite query would be pagination. Give me page 1. When I click page 2, give me page 2. And then all it does is it puts it into the same variable of robot state. hopefully that all makes sense. What we do is we take the initial page parameters, which is about 30 seconds worth, because getting an hour's worth or a few days worth of time series data when we only need to show 1 second's worth is a bit heavy-handed. So what we do is we give it 30 seconds worth, and then when we get close to 30 seconds, we then tell it to fetch another request, give me another 10 seconds. And that's sort of a balancing act between not fetching too often that you're DDoSing your own server, but also not fetching too much data that the request takes too long. So it's sort of a balancing act, and it's sort of, you can tweak the numbers. You could do 1 second every second. We went with sort of 30 seconds on the initial load and 10 seconds on the buffer. And then we have a few ways that we might need to fetch the second or the next lot of data. I define these as sort of a soft seek and a hard seek. There might be a better term for it. A soft seek is when you follow on from the previous second. So that's when you, if you've ever watched a YouTube video, when you go from 1 second to the next one, to the next one, to the next one, that's a soft seek. And a hard seek is when you skip from one point in the video to another point. Might be forwards, might be backwards, but it's a big jump. It's not consecutive. It doesn't follow on. So when you're close to the end with a soft seek, we know that when you're 10 seconds from the end of the data, go and fetch some more. If we do a hard seek, then we might have the data, because you might have kind of jumped 20 seconds. I'm sure we are within that data. Or you might have jumped to 3 minutes ahead, or 2 hours ahead, or 5 hours back, or whatever. So when we ever do a hard seek, we just reset the query with the new parameters of the new point in time that you jump to, and fetch another 30 seconds. And then again, when you start playing the video, it all works. So the next problem is actually being able to loop through in some sort of game loop to be able to go from 1 second to the next in a way that makes sense over time. So instead of it being like a chart, and you might have your mouse hover over that chart and give you specifics on the value, because we've got so much, we opted for like a video player replay like system, and so we need a loop so that every second go to the next event. But we need to understand how we're actually going to manage that state. So first I'm going to jump into a little side quest. Jetai is a state management library, and the reason why I'm not using React's state management library of just kind of use state is that React is really good at being fast when state updates, except when you update state too quickly, which feels like a bit of an oxymoron to say. But the way that React works is it has a reconciliation process. So if you think of all those notes on the piece of paper that's lying flat, almost circled, there's nodes in the DOM, or nodes in the shallow DOM, in kind of the way React handles it. Whenever we make a state change, it compares the two trees and it goes, only this node's changed, and then at the commit phase, it will then update the HTML. And that bit is the reconciliation phase that can be really slow. The commit phase is really fast, because actually if you just updating DOM nodes, you can actually do it really quickly. And most of the time, we're running 3D stuff in 120 FPS, and it's nice and smooth. So we know that React can be fast, but the reconciliation process can be slow, because it's comparing an entire tree to an entire tree. Obviously, we've only got 6 nodes here. If you've got 6,000 nodes, it gets a lot slower. And if you're trying to update that, or do that reconciliation process 60 times or 120 times a second, React just doesn't work. And it's one of the gripes that people don't like about React, is that when it comes to animations, React's actually quite poor. So I use a library called Jetai. It is basically built up of little atoms, so they're the 3 at the top. They sort of exist in a layer above your application. And what that means is that when a component sort of subscribes to an atom, it handles the optimization very easily, because it just says, has this one atom changed? If yes, we render that component, and only that component. Jetai also has some other functionality called transient updates, which means we can get the value of the atom outside of React, and if we need to do things at 60 FPS plus, then we can actually access that atom without React ever knowing about it and update the DOM, but also React sort of kept in sync as well. So that's the reason why. Most of this is a bit overhand, like sort of overkill for what we're doing here, but essentially it means that we can get buttery smooth animations on the play bar. It also means that we can kind of update things, and instead of looping every second, we actually loop every 16 milliseconds, so that we can be sort of faster when there's an update. Because, like I said, we don't actually know if things will update every second. They might happen at 2 hertz or 10 hertz or 60 hertz. So, not knowing what the limitation is, we need to loop as quickly as we can. 16 milliseconds is 60 times a second, and so having a system that we know can update that quickly is really important. So, hopefully, this is going to make sense. But we have an atom, a state data pointer, which is just a number, it goes from -1 to x. And we have an API that is very, very similar to useState. If you substitute useAtom for useState, it is exactly the same. So anyone that's used React, hopefully this is familiar. For anyone that hasn't, here's the data. When you want to update the data, that set pointer is a function. Call the function with the new value. React re-renders, and this value is updated, and you have it. Hopefully that all makes sense. So next we can actually start to run a loop. So again, in React world, we put it into a use effect. We have a set interval, which I'm running at once a second here, 1,000 milliseconds. 1 second, run some code, and then we make sure we clear it at the end, so that we don't kind of have listeners memory leaking into people's browsers, basically. There is a problem with this though. JavaScript, and this is a JavaScript problem, not a React problem, JavaScript isn't running that code every second. What it's actually doing is it's calling the function, the predicate, the callback function, whatever you want to call it, the bit between these two brackets. It's calling that function once a second, or it's passing that to the microtask queue. It's not running the code once a second. Because JavaScript is single-threaded, procedural, we don't actually know if that's going to run exactly when we need it. So how that actually manifests itself, I'm hoping this can sort of describe it. But the first seconds, 0 seconds, we run that function and everything is millisecond perfect. After a second, it might be a millisecond out. After the second, it's another millisecond out, it might be 2. And the third and the fourth, and we get more and more out of sync over time. And you can sort of see that red bar is drifting further and further away from when it absolutely should have fired. So, a bit of a side quest onto the call stack. So the call stack is a stack. You put things on the top and you take things off from the top. The microtask queue is a queue. Things enter at the back and they work their way to the front, and you pick them off the front. Slight difference there. What's happening here, hopefully I can describe this well, we're currently running on function C. Something is being added on function D into the microtask queue. And that's our loop. That's our function that we want to run. But it's not quite there yet. We're still dealing with function C. Function C is finished. Now, the way that JavaScript sort of handles this in simplified terms is it can either add something grab the next thing from the call stack, or it will check the microtask queue to see if we need to pick something up from there. This is kind of simplified. There's other things around like request animation frame, which also sort of lives separately, but it's all about how it picks up the next piece of work. And in this sort of simplified idea, the next thing is off the microtask queue. So we've moved it onto the call stack. We then run that function, and then we continue onwards. So that's what's happening here, is actually the set interval is taking this function and passing it on to the microtask queue every second. That doesn't necessarily mean it's going to fire every second. And so what will end up happening is on the right hand side, this is an actual kind of log of what's happening, all the numbers there aren't 1,000. And that's the problem. Sometimes it's 999, sometimes it's 1001, sometimes it's 1002. Oh, so that's only 2 milliseconds over on a 1 second period. But if that's 2 milliseconds on a 16 millisecond interval, that means potentially every 8 iterations, you are now 1/16th out. And it's going to add up and add up and add up. So hopefully that gives you an idea of part of the problem with running loops in JavaScript. There is actually a better way of doing this. That ultimately the set interval is actually running in the background. So if you've not got the tab open, technically this is still running. I didn't find out about this until after the project, and I haven't changed it yet because the use case is valid, but it's not a major problem. But what you actually do is instead of running a set interval, you actually run a set timeout, and then you work out the difference between each one, and you fire a new set timeout. And once that fires, it calls itself, which fires another set timeout. And basically that will ensure that if it is in the background, it won't keep running, basically. For us, the loop's only running when you actually press play, so it's not a massive use case, but yeah. So for what we want to do, and tying it back into how we actually got the data, we have a hook called useInterval, and right at the bottom we've got that 16 milliseconds, so that's our iteration loop. Nice red number at the bottom, that's our 60 times a second. We are going to get the current tick, and we're going to compare it to the last tick. And this is where the transient updates comes into play. The store.get is getting the atom value from Jotai, and it's doing it completely outside of React. So it doesn't matter how often the current time actually re-renders in this component, the component won't re-render, but we can still access it inside that loop. So it gives us really, really good fine-grained control for when we want to access stuff. And just accessing an atom is really cheap, so you don't necessarily have to worry about performance there. We essentially check the difference. We use a library called DJS, and it has a diff function, which literally gives you the difference in milliseconds or days or hours or weeks, whatever you want to do. We want it in milliseconds, so we get that difference. We then pass that difference onto the last tick, and we update the current time, because we know how long it's been since the last time we called this function. And then we do some stuff related to the data. We basically say, if we are within 10 seconds of the end of our known data set, go and fetch some more. And that's that fetch next page function we call. And then what we also need to do is we also need to update a pointer. So the way that I implemented it was, we've got this time series array, and it is an array of data. Because this is a soft seek, we know that the next interval followed on from the previous one. You don't need to look through an entire array to know if you need to go to the next array. You can just check the next array and see if you're past when the timestamp of that event was, or when that interval was. So that's what I'm doing here. We have an array of data, and we have a pointer, and when you're on the first second, you're on pointer 0, and then when you're on after 60 intervals, because we're 16 milliseconds or 60 times a second, after the 61st interval, if you like, we are a second ahead, and we should now be on. We should now be ahead of the next item on the pointer, so pointer 1. So that's what we're doing here. We're checking: are we after the timestamp of the next bit of time series data? And if you are, increment the pointer. So it's a nice cheap way of moving through this time series data without actually having to loop through the array every single iteration. There might be better ways of doing it. I just went with this one. It ties in quite nicely with when you're doing a hard seek, because whenever you do a hard seek, you should always be at pointer 0. And if you're not, this will just kind of move it along very quickly. You probably won't notice anything. There's definitely some edge cases around this, but it's important to know, I mean, this was 2 weeks of work for 2 of us, so it was nice and easy just to get something out there, and we can iterate on it later if we need to. But hopefully starting to see that loop build up and how we fetch more data and how it updates the state. Here's the transient updates bit that I put in. Here's another example of it. Again, when we get from the store, it's updating the current time. And the actual atom itself isn't going to update. So even though the pointer is being set here, so you can sort of see, yeah, you can see here, that is using the actual kind of callback from the atom here. So instead of set pointer, it's using that function, which means when this value updates, the component re-renders. It's nice and easy. So it's probably worth me showing what actually all that ended up like. So I'm going to jump out and go and do a demo. If I can find where my mouse has gone. Oh, if I lose connection, the robot's just lost connection. It is like better. Or have I lost internet? Is it me? It's me. So we use a system called Tailscale. It's like a VPN, so you can't actually connect to these without kind of access. For some reason, it just crashed, and that's actually what the problem was. So if I bring this up over here, this is our robot. We have that chart. We have things where they aren't. There's no video data available, and all of this was the robot doing stuff whilst I was just talking. So I'm just going to pick a nice point in the middle here, and we can see there's another robot in the way. But if I hit play, and then we can actually speed this up. So
Robot wars.
So at the moment, I may have just broken somebody's task, but we'll see. Nobody's pinged me about it. We'll skip on ahead. So now we're in a different point. But the important thing is we can know exactly what happens. I go back. There you go.
Oh, wow.
So we'll give it a second. So ours is reversed. Theirs goes back. We're following it. We're trying to get ahead. Trying to capture it, and we can know all of this as it's happening, even though we weren't watching it at all. I was looking at my slide notes. You guys were looking at the slides. We can see all this happens. I will just double check that it's not still running missions. Back over. But yes, that's that. Yeah, there's no more missions, and all those missions have failed because it couldn't complete them because there was something blocked in the way. And that obviously was another robot because it's in our warehouse. We have a lot of people running things for testing and things like that. And we ran into a problem, and if this was a production robot, we would get alerted that there was a problem. We'd be able to intervene within the time frame to make sure it can move on. And for us, obviously, it didn't make sense for the demo, but we were able to keep track of it sort of in the past and know exactly what happened, how the robot behaved, and that's all backed up as well by ROS data. Like if there's an incident, we'll grab the ROS bag and we can investigate even further into all sort of the low-level robotics data that we've got. So that's that. That was a good demo, I think. So, what time have we got? We've got on a little bit of time, I think, if Tash is all right. So I wasn't sure if I was going to get time for these, but I think I will. So, there's a few performance tricks. So, as I said, I really love Jotai. It's really handy. You can build up from small atoms, or you can have one big massive object, and then you can actually like scope into smaller parts of the object, and it will handle all the optimizations to make sure things don't re-render needlessly. Super nice. One thing that is really handy to understand with Jotai is about objects or kind of reference equality. So if you have a string and you give it another string that is exactly the same, those two strings are equal. If you give, in JavaScript, you give an object and a second object, even if those objects have the same properties, and those properties have the same values, the objects are not referentially equal, and so they will differ. which means you can do cool things like when you've got a string, if the string hasn't updated, even though this atom has updated, the component won't re-render. So let me try and explain that again. So we had the current time atom previously in the loop. This gets updated every 16 milliseconds. This timer atom, which gets the format of the current time in something readable, this is derived from that value, which means this function is going to also update every 16 milliseconds. But you might think, well, that if you're then putting that into a React component, that's not very efficient. But actually it is, because Jota has inbuilt sort of optimization around referential equality. Because we're only doing to the second and not the millisecond, if the value up to the same second is the same, the component won't re-render because the value hasn't changed. So this is going to rerun every 60 times a second, every 60 milliseconds, but React won't update. And this is nice and fast. You don't really care. Obviously, there's a limit to that. If you've got lots of derived things off of this, there probably are more efficient ways to do it. I did actually have a more efficient way to do it, but the code was a lot more complicated. So I actually opted for this and refactored it into this because it was way simpler and the efficiency was enough to get by. Obviously, if you're trying to scratch every little performance itch, then you can work around that. But this will get you 95, 98% of the way there. So you can do some really cool stuff like that, where this only updates once a second, even though this is updating 60 times a second. That's a really nice performance improvement that we can get there. And then we do the same trick here, again with object kind of referential equality. What we're putting in here is a spring value, and if anyone's used sort of React Spring, it's an animation library. Again, it handles moving all the complicated fast updates outside of React, which is kind of ironic. But if you think of just the spring value as a class, it could just be any class named spring value, and it's a value from, or it's any number. When I update the progress spring atom, so again, this might be updating 16 times a second. You can see. So if I update the spring value, I'm updating the value inside the class. I am not updating the class. So Jota sees an old class and an old class, and it goes, nothing's changed, so we don't need to update. Which means when we come to actually use that value, we can use this interpolator to basically put it into a style. But the progress spring isn't the value, it's the class that contains the value. So this component actually, React never sees the update, but the DOM does. So you can use Jota really effectively with referential equality to really fine-grainedly control when React re-renders, but still keep the UI updating as quick as it can, either 60 or 120 FPS depending on what screen you've got and things like that. So there's a couple of sort of neat performance tricks about why we use Jota and not just use state, because this is not possible with state. It just would not work. So, yeah, that's why. Like I said, it is slightly heavy-handed. You could get away with it. We use Jota elsewhere, so it also makes sense to use the same state management library here, where kind of Jota is absolutely critical to our application running performantly, in a performant manner. Performantly is not a word, is it? But yes, there's some nice, neat tricks there about why we did that. It isn't just a simple problem of like, here's a kind of glorified chart. I just need to update once a second. There's a few more bits to it that are required for a React application at the very least to run in a performant way. Other libraries like Vue, you wouldn't have to do as many workarounds because it has a different model. And if you try to do this in jQuery, good luck, because I feel like it would probably just get unmanageable. So we can get the best of both worlds of React's kind of ecosystem, its component libraries, its its mental model for how it updates things immutably, and we can still do things in a performant way for running at high frame rates. There's a few bits of further reading. So React Query was the data fetching library that we use. GRTI documentation is there, and the perfect set interval is on this YouTube link. It's on the Chrome developers channel. I think it's like JavaScript the hard way. It explores the reasons why you might not go for a set interval. You might do this sort of recursive set timeout instead. Like I said, I haven't actually done that because our use case is good enough with it, but in other applications that might not be the case, and you might want to look into it. But that's it. So if you have any questions, I'm happy to answer more questions about the robot, what it does, what it can do, things like that as well. Obviously for time, try to keep this very focused on the particular project that we did a couple of months ago, me and a colleague. But yeah. Any questions?
Can the robot dance like the
It lacks arms and legs, so
It's got lights on it.
It's got lights. It's got multiple lights. It's got blue ones like a forklift to tell you it's coming around the corner, and it's got lights for the scanning. Yeah, I mean you could strobe them, I guess.
Yeah. That'd be a great promotional video.
Yeah, just spin around.
Yeah.
I'll pass that feedback on. We need a party mode.
Has it harmed anybody? Has it harmed anybody and broken any of the 3 rules?
Short answer, no.
It's not self-aware yet.
Well, ultimately, it's not self-aware. We do use AI, but a lot of the logic is more about if statements, reading the environment around you and performing in a known sort of constraint. So you really have to force the robot to crash into a wall. Like the robot is very specifically designed that even if because you can drive it manually, even if you drive it manually to the wall, it will not drive into the wall. Like you have to turn off all the safety features, and even then, you can't turn off some of them. Like it's very well protected around even a person trying to maliciously drive it into something it shouldn't. It won't. It drives at about ½ meter a second, so it's not particularly quick. Every instance that we've had with forklift driving into it, it's been a forklift driving into us, not us driving into it, and we have proof of these occasions, which is very handy. We get a few knocks here and there. We've had one very serious one that required sort of recovery of the robot. It broke the tower and stuff. But yes, so the answer is in short no, and in long sort of no as well. There's a lot of safety systems, and the AI sort of LLMs and the things that we use, the black boxes, they aren't used for the autonomy of driving. It's more used for the analysis and a lot of the analysis benefits you get of LLMs and stuff. One of the use cases of that is around palettes. So if anybody knows anything about palettes, the blue ones are special. And sometimes they're brown, sometimes they're red, but the blue ones are special. They mean they're rented, and they can cost thousands if you've got lots of them. They cost even more if you break them. So knowing exactly where all of your rented palettes are is really important. So what we have a sort of AI algorithm that runs through image processing to tell us, is this palette blue, red, green, wood, whatever, and we can tell you where every single blue palette is in the warehouse, which obviously for companies is a massive benefit. So we do use AI, but like I said, for core fundamentals. We don't, because it's such a black box, and obviously we've all seen Teslas drive into walls and things like that. So yeah. Any questions?
So you mentioned the basic analysing the warehouse, what's in where. Is there any other functions it does, or can do, or plans to be done?
We're sort of very much focused on warehouse logistics, sort of analytics. So everything we do is within a warehouse. We have a few different systems. So there is a rack, which you kind of saw at the start. Think of a big sort of structure with holes in. You put a pallet here, and it's full of shelves and pallets, all the way up. There's also another type of storage system called block stacking, which is where fridges, ovens, TVs they don't have any like physical structure to stack them. They are literally stacked one on top of the other. So you've got an entire bay of fridges, and they are stacked sort of 3 and then up 3 and then back. That's 14 meters maybe. So the difference, there's a lot of challenges with that because racks give a lot of detail to the LiDARs. They are very intricate, there's lots of it, it's all over the place. You're often between 2 of them, so things like localization to make sure the robot is actually, or where we think the robot is exactly where the robot is. That's really easy. When you're in a rack, the more detail the better. In BlockStack, they're just sort of empty rooms with marker tape on the floor to designate a bay. There's not much in them, so localization is a bigger problem. So we've had to solve that problem and things. There are other use cases that we can fit. Some of the R&D stuff we've got around like thermal imagery, so we can tell if there's any hotspots in pallets and stuff like that. We've got, as I said before, like volumetric analysis. Because we've got LiDARs, we know exactly how full a pallet is, and we get further information from customers like their item sizes. So we can use that to determine how many should be there in terms of not just how many pallets there are, but how many boxes are on this pallet, things like that. So yeah, it's all around sort of warehouse analytics, but there's quite a lot of use cases within that. That essentially the robot is just a means to an end. Like technically, if you could have a human do this, the company would still exist because it's the data that we want. The robot is just a way that we gain or gather that data. But if you could have humans do the same job, which you can't, it's not efficient in any way, shape or form, then you could use that.
So it's more sort of analytics gathering as opposed to like doing the jobs in the warehouse, like
so we don't.
Like picking or anything like that.
Yeah, no, we don't have autonomous like forklifts, although companies like that do exist. But yeah, we're just focusing on that. But yeah, you can certainly have autonomous forklifts and autonomous robots that will move pallets from A to B, things like that.
Did I understand it correct that all operational logic you wrote in React, JavaScript React?
Yeah, all that UI is in React. The backend for our application is in Go, but a lot of that is just robotics gets a bit complicated. So we have obviously a lot of like IoT devices and sensors on the robot. They communicate that to a Go backend, and the Go backend will then do something with that, either surface it to the front end, or in this case, it will store it once a second into a database, and then obviously when we query it. But yes, all the UI for all of our applications are in React.
Yes, this is interesting and impressive because I probably was wrong because considering that for roboting things more suitable like low level language as a Java, C++, and so on, and impressed because before I partly learned React, I just thought that it's for website and user interface, and I'm curious how logic is divided into backend and front end, and what can do you front end, because I read so many complex functions, they are belong to front end.
Yes, so you are sort of right. We do have quite a widespread sort of language ecosystem at the company because we sort of picked the language that fits to the tools and has the ecosystem there. So a lot of the point cloud stuff, we have libraries in C++ because those are the libraries that other people have written and are easy to use, and we can kind of do our job faster. All the UI is built in React. Like I said, the backend is Go. So you are sort of correct in saying a lot of the robotic stuff is not in React, but I think React sort of does make a very good use case for surfacing all of that data. I mean, React was built by Facebook to create Facebook, and if you think of how interaction heavy Facebook is, this is also very interactive heavy. And so for brochure websites where you've just got like a marketing page, yeah, React doesn't really make sense because that interactivity you haven't really got. People are just reading things. But for here, I think it makes a really, really good use case because all the benefits of React we are actually like gaining and actually utilizing. So you are sort of correct in saying that React isn't on the back end and isn't getting all that low-level data, but it does make it kind of really easy to surface that data to the browser and make it comprehensible and usable and quick to build. Like I said, that UI was 2 weeks worth of work. 2 weeks for me and 2 weeks for the backend, kind of running simultaneously. So to have something sort of 0 to 100 and production ready, I think is not bad. Maybe AI would have done it quicker. But I mean, trying to describe that to AI is also very difficult. I think, yeah, and there's a lot more interactions and UX than I showed in terms of the code. Like I showed a fraction of it. There's a lot of interactions around what happens when you get to the end and you haven't got the data yet, and pausing and things like that. And yeah, there's a lot I didn't show, just because of time and kind of being able to understand the important bits. But yeah, React is very versatile, and when you combine it with libraries like Shotai and like React Spring for animations and stuff, it basically becomes the best platform out there, I believe. As I said in the start, I'm a React fan. That's not to say that other things like Svelte or Vue and stuff wouldn't be able to do what I've just shown. They can. I like React, and it fits with the way that I think about code. So